All right, here's example 3 of our series on conservation of energy examples. In this case, I'm going to solve the same problem I did in the previous video, but now I'm not going to let the slide be frictionless. There's going to be some coefficient of kinetic friction here. All right, so what do I have going on? If I'm going to have a friction, I'm going to need to figure out, well, okay, first of all, let me write down conservation of energy. Initial kinetic plus initial potential plus work due to non-conservative forces is equal to final kinetic plus final potential. In this case, I've got friction. Friction is prime example of a non-conservative force. And so I'm going to have a term here. Before, when I had no friction, this term was 0, but now I've got to figure out what the work due to non-conservative forces is. Let me go ahead and make some simplifications first. If I'm starting from rest at this height h, then maybe we've seen the process enough now for me to go fast. And I set my 0 point here at the ground. My final potential is going to be 0. My initial kinetic is going to be 0. And what I'm going to get here is from the initial potential mgh, and that's going to be equal to 1/2, well, plus the work due to non-conservative forces, 1/2 mv final squared. Right, I can't cross the m's out yet because I've got a term here I don't know. What my strategy here is I'm going to go up to the side and figure out what that work due to non-conservative forces is and then come put it back. So let me go down here to the bottom of my page and do some side work, or bottom work as this case may be. I know that work is equal to the integral from a to b of f dot dr. First thing I'm going to do is ask myself if I can simplify this. And I'm going to have a constant force because friction, kinetic friction is a constant force, of course. So what I'll say is the integral from a to b, take that friction force out of the integral. And I should point out that, the displacement is down the ramp. Friction force is going to oppose that. It's going to be up the ramp. I've got a collinear force and displacement. So my dot product is just going to give me F dr. There's going to be a negative sign too. But what I'm saying is I don't have to worry about any angle. So this just becomes a multiplication of the magnitudes. All right. So I get a negative sign from the cosine of the angle. Force of friction times the integral from a to b of the displacement, dr. Well, the integral of dr is just r, or if you want to think about it, the integral of dx is just x. And so what this is going to give me is the length of the ramp. I don't need to integrate to find that out. I can do it with some trig. Sorry, this is going to have to be at an angle theta. I forgot to put that in there. I can do this with some simple trig, right? Here's the thinking I'm going through. Integral of dr is just r, or integral of dx is just x, whichever you prefer. That's just going to give me the displacement. That's the length of the slide. I can get the length of the slide from trigonometry. Let's call it, let's say, I don't know, L. It looks to me like, looks like the hypotenuse of a right triangle to me. So I know the opposite side of this, and so it certainly looks like L is equal to h sine, no, sorry. H is equal to L sine theta, which means then that L is equal to h over sine theta, right? Basically, I decomposed it the other way. I'm used to taking a hypotenuse and decomposing it into sides. In this case, I know the side. I need to recompose, maybe, into the hypotenuse, which is going to get me h over sine theta. So I can do the integration if I want to, I suppose, but when I do, I'm going to get this expression. So it looks like the work due to the non-conservative forces is equal to negative force of friction times h over sine theta. Hopefully that's clear. All right, so, and negative makes sense to me because it's friction. It's taking energy out of the system, right? So what this is telling me is I have this initial energy. I'm going to lose some due to friction, and that has to equal my final energy. I should expect that my final energy, the summation of these two terms, is less than these two terms because I'm subtracting some work out. All right. Now, of course, I need to figure out what the force of friction is. That's going to be, do some more side work. Force of friction we know is mu k times the normal force. At this point, I'm going to rely on the fact that we've done enough inclined plane problems so far for you to see that the normal force is going to be mg cosine theta. If that's not obvious, please go back and watch some videos over inclined plane problems. But when I resolve gravity and the normal force and use Newton's second law to insist that there's no acceleration off of the ramp in the y direction, I'm going to get that the force of kinetic friction is mu k times the normal force is mg cosine theta. Okay, now with that said, let me put that in here, and I don't think I've left myself enough room. I'm going to have minus, in fact, I haven't left myself enough room. Let me just do this. mgh minus force of friction, mu k, mg cosine theta, times h over sine theta is equal then to 1/2 mv final squared. So a little bit more complicated than my previous situation, but not that much more complicated. This is just the frictional force times the distance over which it's applied. Frictional force is mu k mg cosine theta times h over sine theta, which is the length of the ramp. Of course, if you're given L, you just put in L here, no big deal. All right, now I'm in a position to do some canceling. Looks like I still have an m in every term, so I can get rid of that. Looks like I'm going to, again, multiply by 2 and take a square root. So let me pull out let me do some factoring over here. I've got a GH here, I've got a GH here. So what am I going to get here? GH times 1 is left here, minus mu k, right? Mu k, there's my GH, times the cosine of theta over the sine of theta. That is the cotangent of theta. And that's equal to 1/2 v final squared. Now, let me multiply by 2 and take a square root. And I get v final is equal to 2gh, that's familiar, times this expression, 1 minus mu k cotangent theta. Let's see if we can make some sense of this. In previous two results where I had no friction, I found this to be the case. V final is equal to root 2gh. I said because of the force of friction, I'm going to expect to lose energy. That is, I expect my final velocity in this case to be less than my final, I should say speed. My final speed in this case to be less than my final speed previously. Well, this is my final speed previously, and now that is reduced by this amount. So that matches up exactly with what I would expect. I get the final speed is root 2gh times this friction term, right? And the friction is what's taking energy out of the system. So this makes perfect sense to me. I feel pretty good about this result. Again, I think this is a lot easier than going through kinematics. This is a little bit more complicated than the other one, but the work energy has a lot to help us with. Did we have to do Newton's second law down here? Yeah, if you don't remember that the normal force is mg cosine theta, you might have to do a little Newton's second law. But in the end, we got this answer in a pretty straightforward manner. So this is a really good problem for you to practice. I would recommend going through the steps until you understand them.